the second subtopic under first order circuit is source-free RL. So for this RL circuit, we are interested to find current, current through the inductor compared to the RC. In RC, we search for VT, but for RL, we are interested first to find the current. So again, this I0 is initial current, and the energy stored in the inductor is half Li square. And if this I is initial energy, initial current, so it is symbolized as I0. So based on this circuit, basic circuit of RL, we can use KVL, positive VL plus positive VR will equal to 0, or actually you can transform into L di over dt plus IR. Why we need to transform this one? Because we are interested to find the I, the current that flow in the inductor. From this, there is no current, but here there is a current, I. Current term, yeah. Okay, so based on this, L di over dt plus IR, then from the differentiation, you need to integrate, and finally you will get ln. And lastly, to produce the main equation for RL, I0 E negative RT over L. This looks very similar to the RC. The only difference is here, I0, because in inductor, we're interested to find the current, and the tau here will be L over R. Different from the RC. Okay, so the current for the voltage across resistor will be the value will be same like the VL, but with reverse polarity. And also we can calculate the VR according to this formula. This formula is produced by I times I that is flow through the inductor will flow to the resistor, I0 RE negative T over tau. Yeah, this is the formula just now, and multiply with R. And then this also manipulate this formula, be creative, and then just pick VRI, I is here and VR is here, just multiply and you will get this one. And energy absorbed by the resistor is the formula looks very similar to the energy stored by the capacitor. The only difference is this one and the tau. Okay, next, this is how the graph of source-free RL. If in capacitor source-free RC, the amplitude here is V, but here RL is I versus T, and still the slope shows the decrement or the value of current that drop according to the time. At T equal to tau, which is tau here L over R, the current here dropped to 36.8% value. Okay, the concept here of RL is very similar to RC. Just RL interested more on finding the current, but RC is more interested in finding the voltage. Okay, let's check on example 3 here. Assuming that IL is 10 ampere, calculate ILT in the circuit below. So IL, we can draw here the arrow or the direction of the current, IL. This is initially stored energy, initially stored current in the inductor is 10 ampere. Based on these equations here, ILT, I0 E negative T over tau. Okay, so we can directly insert the formula, which is 10 E negative T. Our tau is L over R. So 10 E negative T. Our L is 5 over R equivalent here, R equivalent here. You need to start from here. Make it this one parallel plus series. 10 parallel with 40 plus 12 here. Okay, but okay, here is more detail. It's more detail on the explanations. But this is also almost finished. This is also almost finished. Just try to calculate this one. Okay. Okay, so very similar like what I've explained. And finally, we'll get 20 ohm, L over R Thevenin, 0.25 second. Directly insert the parameter, this parameter, and this parameter. So finally, we'll get 10 E negative 40 ampere. Maybe you can try by yourself exercise 3. But this time, try to analyze T less than 0 circuits and T more than 0. Okay, because here the switch is open when T more equal and more than 0. So you need to find when T less than 0, what is the I0 current, initial current stored, and at this point, under these conditions, the parameter that you need to find is R equivalent, because here you want to find the tau. Okay. Example 4. Assume that initial current for this inductor is 10 ampere. Calculate IT and IXT that flow through this 2 ohm resistor in the circuit below. So this circuit is quite difficult because it involves dependent source, which is voltage source controlled by the current here. But this circuit also use the same formula, which is I0 E negative T over tau. And tau here is stand for L over R. Okay, this is the formula to find I for the inductor lah. But this one IX, we need to analyze using the current divider. Or once we already know, once we obtain the I, we can proceed to find the IX. Okay, due to this dependent source here, before that the initial value is already known, so we just left to find, we just need to find the R equivalent here, because L is already given. So dependent sources, we need to solve this one. It can be solved using Thevenin or Norton, but I think it's better to use Thevenin, yeah, by replacing this one as a terminal, yeah, and this become I0, because we know that from the inductor there is a current, but replace this one as a voltage. This is the basic concept of Thevenin, yeah. Thevenin, replace this as 1 voltage, replace the terminal as 1 voltage, and there is a current exit the terminal. This one, we symbolize this one as I0, as described detailedly in here. Yeah, okay, this is the terminal. Transform this and become like I0. This is the voltage that we replace, voltage source. This is the step to find tau, yeah, because this is already determined previously at T less than 0, because it's already given in the question. Assume that initial current is 10 ampere. So in order to find the tau here, because we need to find first R equivalent, L over R. So in order to find the R equivalent, we need to transform this circuit into Thevenin. Okay, we're going to start finding the I naught here because the Thevenin formula are equivalent, V over I, this is ohm, but this is how we're going to find R equivalent using Thevenin. V naught over I naught, V naught here is the V terminal AB, here is given 1 volt, divided by I naught. Okay, I naught is same like I1, okay, but we need to find I1 using mesh analysis. Negative for loop 1 here, negative 1 plus 2I1 plus negative I2 equal to 0, and finally we'll get this first equations. And for loop 2, finally this is the second equation for loop 2. When you solve these two simultaneous equations, you will get I1 3 ampere and I2 2.5 ampere. Back to here, remember this is IT, but actually we are interested to find I naught first. Yeah, this is just to symbolize this one, IT, the first term, that the first question that we need to answer. But focus first on finding the R equivalent. So I naught here is actually equal to I1, yeah, 3 ampere. So straightforward, R equivalent is V naught over I naught, 1 over 3, 0.33 ohm, and we can proceed to find tau, L over R equivalent, which is 1.5 second. So based on this, here I1, before finding the I here, we can use insert the parameters that we have found into this formula. 10 e negative t over tau. 10 is already assumed in the initial stage. Okay. After this, then we can proceed to find the Ix. Okay. IT here is similar, 10 e negative t over 1.5. I naught here just to determine R equivalent. Ix here is V equal to, we know that here V equal to L di over dt, voltage for the inductor, and from previous solutions, IT equal to 10 e negative t over 5, because if you know this voltage, since this is parallel, so we can find the value for V2 ohm here. That's why we need to find the VL, which is equal to V2 ohm. Then we can use Ohm's law, V2 over 2 ohm is equal to Ix. That's why first find the VL, which is VL di over dt, and di over dt here is based on the current I, 10 e negative t 1 over 5 over 1.5 here, and multiply with the L here shown here. Directly we can get the VL. So VL here is same like V2 over 2 is equal to Ix. Okay, which is finally Ix is negative 1.667 e negative t over 1.5 ampere. We go to the last example of RL, source free RL. Based on this circuit, find IT, I that flow through this inductor. So in order to answer this, we need to analyze these circuits when t less than 0 in order to find I naught first, then t more than 0 to find the tau, which is to find R equivalent. Then we can find t, tau of L over R. Okay, based on this circuit, when t less than 0, the switch is connected, and the switch is switched on, and this line is connected together. So current will flow like this, and also split into two 2, and then at this junction the current decides to go only to this part. We'll ignore this 5 ohm because this is short circuit, yeah, and this also will go straight forward like this one because this is short circuit compared to this one. There is an obstacle, K, this one, okay, which is depicted here, yeah. The 5 ohm is already not seen, so only 12 and 8 ohm. This considered short circuit when t less than 0. So this is t less than 0. We just need to find the I naught, which stands for the I that flow this inductor. This is the inductor. We don't need to draw the inductor, just find the I naught. So based on these circuits, we can use current divider to find the IT, and we'll get 2 ampere. And then next we need to analyze these circuits when t more and equal to 0. So the line is disconnected. The current source here is disconnected from the circuits, and now the inductor flow through this 12 and 5 ohm, which is represented by this figure B. Okay, from here we need to calculate the R equivalent. So based on this one, set your view here. Set your view at the inductor, and then you will see that current flow we split into 12 and 5. 12 passing 8, so 12 is series with the 8 parallel with the 5 here, yeah, and then go back to the negative polarity of the inductor. So here our equivalent is 4 ohm. We proceed with the calculation of tau, and then just insert back the value to be negative t over 0.5 ampere. So that's the final answer for the example 5.